This is where. There we go. And please let us know if the camera needs focusing, because I don't have my monitor that shows. Actually, I can. Let me put this on. Okay, well, so Happy New Year again. As you can see, technical issues are not just a problem of 2022, but also apparently a problem of 2023. I apologize for this aspect of the course. I hope it hasn't been too disruptive, and I hope having the videos and the Zoom possibility available has made up for this slight, hopefully, disturbance to the running of the lectures. So as you know, there are 2 weeks of lectures. This lecture today is the end of the mainstream material in the course. And as I wrote on the forum yesterday, you should have hopefully all seen the email. Next week's lecture is going to be some more advanced topics of one of the directions in which computability theory is used, namely looking at computability theory as the basis for something called information complexity, that basically Kolmogorov complexity, and something called algorithmic randomness, studying randomness properties of sequences. So there's some nice applications of, these are nice mathematical applications of computability theory. And as I said in the forum announcement, that material is for those who are either interested or it's advanced material just for the oral exam for those people who want to take challenge topics in the oral exam. There will be some of the topics also from the main lecture material will also be ranked as challenge topics for the oral exam, so some of the harder stuff. Right, we'll maybe talk about exams a little bit later. So what I want to do today is end the material on computing with infinite words that we've been looking at for the previous 2 lectures, and now it's the third and last lectures on that, by going back to what I presented as the motivation for looking at this notion of computing with infinite words, which is trying to get a good notion of computability on non-discrete data. For example, and this is going to be now the example of this lecture, what it means to compute with some non-discrete data like real numbers. So we want to look at computability aspects of functions on real numbers, for example, rather than functions on natural numbers. So already in the first lecture of this part of the course, I introduced one approach to that. So we motivated using infinite words because one can represent real numbers using infinite words. So the basic idea today is we can use omega words to represent, in the sense of having representations, actually represent non-discrete data such as real numbers. And once you can do real numbers, you can obviously do tuples of real numbers, so coordinates in n-dimensional space. You can do complex numbers, because a complex number can be represented as a pair of real numbers, and so on. So, you know, if we can compute with real numbers, we can do a lot of things. Of course, one can anyway, in any case, compute with finite approximations for real numbers, like as in floating point numbers in programming languages. But as you know, the computing with floating point representations, where you have a fixed finite bound of the representation, has defects in that you're always making a little bit, when you apply many operations, you have to make some approximation, so you get what are called rounding errors. And actually, these rounding errors you have to be quite careful how you use real numbers with floating point, because the rounding errors can quite quickly multiply. I mean, for example, take some real number and you square root it a lot of times and then square it a lot of times, you won't get back the same number of times, you won't get back exactly the same number that you started with. So the idea occurred to many people a while ago that actually one could be more accurate if one wanted to by computing with real numbers, thinking of them as infinite streams and representing infinite streams on the computer. And in doing so, one can actually do exact computation with real numbers, that you're guaranteed that the computation is correct to whatever level of accuracy you want to inspect it to. And what I'm going to look at today is sort of a theoretical foundation for that. It would have been nice to do there are some online applications that one can demonstrate. It would be nice to include that in the lecture, but I decided I can't quite fit it in. So you can look up exact computation with real numbers if you want and play with some of the tools that are available. But what we're going to do today is look at the theoretical basis for such things. So already 2 lectures ago, we had the naive idea, which is simply, once we've got an omega word, we can simply represent a real number in the usual way as an infinite sequence of digits with a decimal point or a binary point or whatever in the appropriate place. And that should be a perfectly good representation of a real number, because if we've got the infinite sequence, we've got, we're representing the real number exactly using the infinite sequence. So the first idea, but I'm going to call it naive idea because it's going to turn out to be too naive. Naive means not sufficiently sophisticated. It's got some little error of not being suitably careful in your thought, but we'll find out what that is in a moment. So naive idea, use an ordinary base B representation. So B is some natural number here of real numbers. So to make sense of base B notation, you need base to be at least 2. So e.g. decimal notation, the one we usually use. That's B, and the base is 10, as we know. So a real number would be, such as pi, would be represented. So pi would be represented as 3.141592653, and so on. So here, an appropriate alphabet for that would be the alphabet where we need the 10 decimal digits, 0 up to 9, and of course the decimal point. Oh, and also a minus sign. If we're using the ordinary representation, we would have the minus sign, and we would write. It would have rules about which infinite words count as a representation of a real number. So we would, you might say at most 1 minus sign, and that minus sign, if it occurs, has to be the very first symbol of the omega word. Exactly 1 decimal point, and well, I guess that would be all the rules. If you don't have any, that would be sufficient number of rules. And if you don't have any digits to the left of the decimal point, it counts as 0 point something. You've got exactly 1 decimal point. Can't you put the minus sign after? So after the decimal point, you have to have an infinite sequence of digits. Anyway, we won't bother to write out these rules because actually, for any base B, this notation has a significant problem to it. Does anyone know what the problem is, or can you think what the Does anyone have any idea what?
Yeah, I'm looking at this equal, why not?
Well, so that's an interesting point. So you have more than one way of representing the same number. You've got, so for example, 1 could be 0.999999999 forever, or 1.00000. But that in itself is not actually a problem, because we can still have, you know, we know how to compute with representations where you have several different names representing the same element. We've already done that with, but I mean, that's a good point to raise, but actually that in itself is not the problem. Does anyone have an idea of what the problem is? Okay, well, let's find out what the problem is. Is that you can't, if you use this representation, a lot of very basic functions are not computable. So I'm going to give you an example for that and we'll see what the problem is. The proposition using the decimal representation the function that maps x to 3 times x, so the multiplication by 3 function is not computable. That's maybe a little bit surprising. You'd think that multiplication by 3 is very simple, it should be computable. And you might think, well, we even know algorithms to do multiplication using the, you know, when you're at school, you learn algorithms to do multiplication of real numbers. Why can't we just implement one of those algorithms on a computer? Well, the problem with an algorithm for multiplication is it starts at the right-hand side of the number, not the left-hand side. And here we're dealing with infinite numbers, and there's no right-hand side. So we can't use the school algorithms because there's no place to start. Of course, that in itself doesn't prove that it's a multiplication by 3 is not computable, but that's the reason that we can't apply one of the standard primary school algorithms in this case. So let's see why it's not computable. Well, what would it mean for it to be computable? Well, so implicitly here, we're representing real numbers as infinite words. And so the notion of representation being used here is analogous to the representations we were considering before. And what we mean for a function to be computable is that we have a function on representations that, so the 3 times function would be computable if we had a function on representing words that whenever given a word that represents a real number, the computable function on representing words will compute an infinite word that represents another real number, which is 3 times the original real number. So what we're saying is that the function on reals from x to 3 times x, for that function, there is no corresponding computable function on representing infinite words. Now, how can we prove there is no computable function? Well, we've proved in the last lecture that every computable function is continuous. And what we're going to show is that the function x to 3 times x, well, that's obviously a continuous function on real numbers, but there is no continuous function on infinite words that will compute the 3 times function on representations. So the proof is we show is no continuous function, continuous partial function, so continuous on its domain, from that computes x to 3x on anything else representing real numbers. by one of the main theorems from the last lecture. If we had a computable function, it would be continuous. So if there doesn't exist such a continuous function, there doesn't exist a computable function. Okay, so how can we show there's no continuous function? So suppose the contradiction that G is such a function. So then if we apply, so G is a function on infinite words, a partial function on infinite words over the alphabet with the decimal digits, the decimal point and the minus sign, that needs to be defined on all such words that represent real numbers. So that the legitimate syntax of a real number. So if we have such a G, then let's change color. We get to the next stage of the proof. And we know that if we apply G to the input sequence, 0.3333 recurring, so in normal mathematical notation, when we put a dot above the place you recur that, I'm going to use the notation I've been using for finite, well, for infinite sequences here, where I put 3 to the omega just means the infinite repetition of threes here. If we apply it to this infinite word, of course, this is a decimal representation of 1/3. So 3 times a third, G needs to compute the 3 times function. 3 times a third is, of course, 1. So we know that G of 0.33333 needs to be an infinite word that represents 1. And there are exactly two such words. There's 0.9999999, etc., or 1.0000. So either G of 0.333 and so on will be 0.99 so forever, or G of 0.3, and write it so many times, will be 1.00, carrying on forever. One of those two. And we're going to show that any such continuous function G will not does not compute the multiplication by 3 function. Okay? So we've got a continuous function that it either satisfies this equality or this equality, and any such function cannot represent the multiplication by 3 function. So suppose the first equality is satisfied. We've just got 2 cases. But this is one case, and the other case is if the other equality is satisfied. Well, in this case, because G is continuous, remember, being continuous on infinite sequences, this is the property we looked at last week, being continuous on infinite sequences means that for the output value, any finite prefix of the output value is determined by a finite prefix of the input value. So let's consider in fact, it would be enough to consider the output prefix 0 point here, but just to make things clear, I'm going to consider the output prefix 0.9. So because G is continuous, there's some length of input prefix such that any extension of that input prefix outputs G of that outputs 0.9. So because G is continuous, there exists n. such that for any P with, so that's an infinite sequence of input characters with P restricted to n, the first n characters of P equals 0.333. We have, so where this is then symbols, we have G of P, the first three characters of that is 0.9. Okay, so the output prefix 0.9 must be computed by only looking, must be returned by only looking at finitely many symbols of the input sequence. So for any P that begins with those n characters, the output sequence begins 0.9. But then, if we apply G to 0.333 to the input sequence, the particular input sequence where we start off with our n symbols with n minus 2 occurrences of 3s there, and then we continue with 9s from here. Once we get to the end of our n input sequences, that's the result of this application. The first three characters, by what we said, are going to again be 0.9. So the first three symbols of this computation are 0.9. But then, if you look at what this input is, this is a value that's strictly greater than 1/3. But there's no possible way of continuing this sequence to get a value that's strictly greater than 1. But so 0.339 the omega. Sorry, there are n character symbols up to here. Represents a real number strictly greater than 1/3. But the result of applying G to it cannot represent a real number strictly greater than 1. And G of this value represents a real number strictly less than 1. And that's a contradiction, because G is not computed by 3. But one can find a very similar argument for the other case, which is the other case is the one done in the later notes. A similar argument gives a contradiction in the other case. Okay. So the multiplication by 3 function, very, very simple function, is not computable with this representation. If you got a little bit lost in the details, well, you can look at the online notes, but this is also a straightforward way of thinking about it, which is that so if you want to just step back from the details and think about it this way, we're trying to implement a Turing machine to do multiplication by 3. The Turing machine is going to take as its input the decimal representation of a real number. Let's try to be that Turing machine. We don't know what the algorithm is, and we're going to take the input of the real number. And suppose somebody keeps on giving us this input 0.3, and every time we ask for another digit, we get a 3. So we keep on getting 0.3333333, and as long as we ask for new digits, we get 3. But we want to output a value. So at some point, we have to start outputting something. And to start outputting something, well, we're going to have to either output 0, and I mean, eventually we have to output a decimal point. We need to either output 0 point or just point or 1 point. So at some point, we need to do that. And if we keep on seeing 3s, we can never commit, because we don't know if it's going to continue as threes, or if it's going to go down and be a little bit less than a third, or up and be a little bit more than a third. And the problem is, so as long as we see threes, we don't know whether the input is smaller than or greater than 1/3, or equal to a third. But as soon as we output, we're committing to one of those two possibilities, and we can't do that. Okay, so you might conclude from this, well, the very idea of computing with infinite representations of real numbers is a loser, is not going to work. Of course, that's not the case, otherwise I wouldn't be giving this lecture. Does anyone have an idea how we might fix this? So at the moment, it might look like the problem is the problem that you mentioned, because it looks like we're actually having problems because we've got two representations of a real number. But that's not really the problem, because actually the solution is to have even more representations of the same real number rather than only two. Well, anyway, the problem is to change representation. You might say, well, the base 10 representation is unnatural. What about binary representation? That's more natural for computational purposes. But actually, with binary representation, again, you can't multiply by 3. And in general, for any base B representation, you can only multiply by numbers that I think that are products of prime divisors of your base. I believe that's the correct. I believe that's the correct general formulation, although I've never seen it anywhere, and I've never stopped to actually prove it myself. It would be a good use of time. Anyway, so changing the base doesn't work, so we need to have a different representation of real numbers. So what we're going to do is we're going to define such a different representation, and then we'll have a break. And the representation we're going to use is quite a little bit more elaborate. But on the other hand, it's quite natural. We're going to use instead a representation which I'm going to call a Cauchy representation. And the idea is to represent real numbers rather than as digit sequences, as Cauchy sequences. Cauchy sequences of rational numbers, and to have rational numbers that we have nice, easy representations for, we're going to use dyadic rational numbers. So I'll say what that means in a moment. So a real number is represented as a Cauchy sequence of rational numbers. So as I said, rather than arbitrary rational numbers, we're going to use dyadic rational numbers. And actually, rather than arbitrary Cauchy sequences, we're going to use Cauchy sequences that have a fixed, rapid rate of convergence. And we're going to call such things fast Cauchy sequences. Okay, firstly, what is a dyadic rational number? Dyadic rational number is a rational number so any rational number is expressible as an integer fraction. That's the definition of rational numbers. Expressible as an integer fraction. But does anyone know what the characterizing property of dyadic rational numbers is? Sorry? Yeah, very good. I think you might have already represented dyadic rational numbers in an exercise class a few weeks ago. So an integer fraction whose denominator is a power of 2. Denominator is the bit on the bottom side, on the bottom of a fraction, and the numerator is on top of the fraction, whose denominator is a power of 2. And the fast Cauchy sequence, well, we'll see what that is when we get to it. So we want to represent a real number as a Cauchy sequence of dyadic rational numbers. So firstly, we need to represent dyadic rational numbers, but that's something you already did in the exercise class. Maybe I'm going to use a slightly different notation here. But I'm going to use, I think, the same representation as in the exercise class. So we're going to first represent dyadic rational numbers. Dyadic rational numbers as words, as words over the alphabet. So if we're talking about dyadic rational numbers where the denominator is a power of 2, it's very natural to use a binary alphabet for that. So we're going to use the alphabet appropriate for binary numbers. So we're going to have 0 and 1 for the binary digits. We're going to give ourselves a decimal point, sorry, a binary point rather than a decimal point. Separate the whole and fractional parts, and we're going to give ourselves the minus sign. Again, of the form. And let me just look at my notes to see what notation I use. So either so I'm going to, so it's either going to be a sequence of digits, binary digits. These are the ones to the left of the binary point, so doing the Pullman part. And the ones to the right of the binary point, I'm going to index by negative numbers. So the idea is that each of these little b's is a 0 or a 1. And so this should be -4. And the reason for numbering them in this way is that each of the index represents the weight, it represents the power of 2, that's the weight of the number. So yeah, the 0, that's the unit part, that's 2 to the power of 0, that counts 1. 1 here, which will be next to it, counts 2 to the power of 1, which is 2. 2 will count 2 to the 2, which is 4. -1 here, immediately right to the point, 2 counts 2 to the -1, that's a half. This is a 4, this is an 8, and a 16, and so on. So these are the positive numbers have this representation, or negative numbers have this representation. So again, similar to before, we just put the so where n is greater than or equal to 0, so that means you may or may not have, you have some finite number of digits to the left of the point, but it could possibly be 0 digits to the left of the point. When n is 0, there is no d0, according to this notation. And each d sub I belongs to one of those characters, 0 or 1. The point is these are finite words. So actually we go up to some d minus n. I hope I've got. I realized I was looking at the notation in my notes and then I was looking at the wrong place. Should be, yeah, okay, that's good. I do have exactly this notation. So we go to d to the minus d minus n, and I guess n is also greater than or equal to 0. Right, so if n is 0, there's nothing on the left, and if n is 0, there's nothing on the right of the decimal point. So it's just the usual representation as a finite sequence of binary digits of a dyadic rational number. And for u of the above form, we define qd of u, that's what I call it. This is the dyadic rational number represented by u. Do I call it qd? Let me just check. Yep. So this is going to be either, I mean, it's the obvious thing. You simply sum these digits, weighting each one according to the weight. So in the case that u does not begin with a minus sign, it's simply the sum from I is minus n up to n minus 1 of di times 2 to the I. So if u does not begin with minus, and if u does begin with minus, then it's just minus that. So minus the sum from I is of the indices from minus n to n minus 1 of di times 2 to the I. So if u does begin with minus. And what we've defined in this way so the above defines a representation of dyadic rational numbers. But you already did this, exactly this representation in an exercise class, I think. So representation QD from I gave the alphabet a name. So this alphabet I'm actually calling sigma B for the binary alphabet. So it's a representation using finite words. Partial, because not every finite word is of one of these legitimate forms. Of course, as every representation, it's surjective onto the set of dyadic rational numbers. So this is dyadic rational numbers. And this is a representation in the sense of the lecture 3, when we considered representations. That's a representation by finite words. So I'm now going to start calling these type 1 representations. These are the first kind of representations we considered, representations by finite words. Of course, to represent real numbers, we're going to use infinite words. As I've told you, that infinite words are going to be Cauchy sequences of dyadic rationals. They're going to be infinite words formed using the components of which are going to be these representations of dyadic rationals. And the infinite words, that's going to be representations using infinite words. Sorry, the required representation of real numbers is going to be a representation using infinite words, so we're going to need a new form of representation for that. And as you can get, I've called these type 1 representations because the new representations are going to be called type 2 representations, just like we were calling the Turing machines that deal with infinite words type 2 Turing machines. Anyway, we're halfway there. We've represented the dyadic rationals. I'll complete the representation of real numbers after the break. It's more or less 3 o'clock, so we shall have the usual break till more or less 3:15. Okay. Nancy, can you start the recording? Thank you very much. Okay, so what we were heading towards was trying to define this representation of real numbers, which I'm calling the Cauchy representation. We're going to represent a real number as a Cauchy sequence of rational numbers converging to the real number, of dyadic rational numbers. And to represent the dyadic rational numbers, we're going to use this representation. We've just defined this representation using finite words to represent dyadic rational numbers. So given that, we can now proceed to the representation of the real numbers. So, so here we use the alphabet, which I'm calling sigma B. Sigma B is the alphabet representing primary words representing dyadic rational numbers. So we have 2 binary digits, the binary point, and the minus sign. We're going to add one more symbol for our representation of real numbers. So we define sigma C, alphabet for the Cauchy representation, to be, well, all the symbols from sigma B, the alphabet for B, together with the semicolon symbol. So another separator, well, a separator here. I'm not using comma because I want to sort of a big separator, so clear. And what we're going to do is we're going to define a type 2 representation. A new type of representation representing real numbers as infinite words. We shall define a type 2 representation of real numbers, which I'm going to call gamma, a generic symbol for representations, sub C for Cauchy. And so that's going to be a representation using symbols from the Cauchy alphabet. But we're going to represent now it's infinite words. So we've got the omega here. So it's the set of infinite words over the infinite alphabet. And by a representation, we again mean a partial, so a surjective partial function from infinite words now to the real numbers. So it wants to be surjective in that we want a representing name for every real number. And it can be partial because we're not going to require that every infinite sequence of symbols represents a real number, just well-behaved sequences of real numbers. Just as with this Cauchy representation, sorry, just as with this dyadic representation, we required the symbol, the meaningful set sequences of symbols, the meaningful words, to have certain lines forward to them. So this is a type 2 representation. Really, the only difference between type 2 representations and type 1 representations is that type 1 representations, we use the set of finite words over an alphabet. A type 2 representation, we use the set of infinite words over an alphabet. In the LaTeX lecture notes, I go through all the definitions again, just to give them for the case of type 2 representation, but I'm not going to spend time in the lecture on that. The definitions are exactly parallel to what we did in lecture 3. I mean, I'll talk through the points as we get to them, but here all we need is we need to define a surjective partial function from the infinite words to the reals. And when an infinite word is in the domain, it is represented, it is a name, or it's an infinite word that is a name for a real number, and the real number it names is what it gets mapped to by the function. So to define a partial function, I need to tell you what the domain of it is, and then what it does on the elements of its domain. So the domain of the function gamma c is the set of infinite words of the form, and I want to know whether I start with 0 or 1 in my notes. 0. So it's going to be a sequence of finite words, where each finite word is a representation of a dyadic rational number. So U0, this is not a single character, this need not be a single character, this is just a finite word representing a dyadic rational number, followed by the next symbol is a semicolon, a single character, separation, followed by U1, another representation for a dyadic rational, followed by semicolon, U2, so we're always using semicolon as a separator, and in between, and then it carries on like that. In between, we have words representing dyadic rational numbers. So let's put all the conditions that it needs to satisfy. So each U sub I is a word representing a dyadic rational number. We can say that concisely. Each U sub I is in the domain of our representation of dyadic rational numbers, of this partial function here. In other words, it is of one of these two forms. So it needs to be a sequence of finite words representing dyadic rational numbers separated by semicolons, satisfying an additional property which says that that sequence of dyadic rational numbers is a Cauchy sequence, and moreover, not just an arbitrary Cauchy sequence, but one that has a certain rate of convergence. So the sequence U sub I, where I is indexing the whole sequence, so I ranges from 0 upwards, satisfies, and I'm going to, I'm sure almost everyone in the room knows what a Cauchy sequence is, but because I need this additional rate of convergence property, I'm just going to state the property that I'm going to ask for. So this is, we're going to ask for all, let me just see which way, what I call things. All n and n in the sequence, where n is greater than, so n is further along the sequence than n. We ask for the distance between the dyadic number represented by U sub n and the dyadic rational number represented by U sub n. So the difference between them is the absolute value of the difference. that we ask to be less than or equal to 2 to the power of minus n, so 1 over 2 to the power of n. Okay. So the general Cauchy property would be for any epsilon, there exists some n such that for any n beyond it, the distance is less than or equal to epsilon. But we're requiring a stronger property than that, which is from any n onwards, things are, all the values are within 2 to the minus n of each other. So they're very, very close. They quickly get very, very close together. So we call this the fast Cauchy property. And we need to define what the representation is, what the representation function is. So what I wrote on this board, I'm just specifying domain, those infinite words, this property with this property. So the representation function is then defined by, so we need to say what representation function does. It is to interpret such a sequence as a real number. So the sequences it's defined on are those of the form that we've got, that we're asking for. So these infinite sequences of names of dyadic rational numbers separated by semicolons. And what's the real number it's going to represent? So I realise it might be have been a lot of symbols for some of you, but I'm sure some people are able to give me, somebody must be able to give me the answer of what we're going to, what real number is such a sequence going to represent? The limit. The limit I of the rational numbers. So we've got a Cauchy sequence of dyadic rational numbers. The rational number represented by u by. And that's it. That's our Cauchy representation. So it's a little bit more complicated than the base 10 representation or the binary representation, but it has a distinct advantage, and that's that it works. And in practice, so there are many packages for that one can, many software packages for this exact computation with real numbers based on this kind of theory, using essentially infinite streams to represent real numbers. And Cauchy sequence representations similar to this are one of the representations that people actually, things quite similar to this are actually used. But it's not a bad representation in practice. I mean, there are, one needs to tune it a bit, and there are other considerations than actual implementation. But anyway, this is not totally divorced from practice. Right. So, maybe let's convince ourselves that it is a representation. So the first statement, well, for it to be a representation, well, it's clearly a partial function as defined. The only thing that remains to show is that it's surjective. So gamma sub c is indeed surjective. So every real number has a representation. Now, I actually proved this in the notes, but all we're saying is that every real number arises as the limit of these dyadic rational interpretation of a sequence of names for dyadic rational numbers. It's very easy to see this, so I'm not going to write it down, I'm just going to say it. So firstly, we observe that every real number is the limit of a Cauchy sequence of dyadic rational numbers. In fact, if you just represent the real number in binary notation, just using the ordinary binary notation with the infinite thing, then if you successively cut off the binary notation at longer and longer binary expansions after the binary point, you get a sequence of dyadic rational numbers that converges to the real number. Moreover, if you do that in the sensible way, starting at the decimal point and then counting to the right, it satisfies this rapid Cauchy property. So it's easy to see that one gets such dyadic rational numbers, and in doing that, well, we're using binary representations, so we're actually giving ourselves the names of those dyadic rational numbers on the way. So actually, we get these the sequence of U0, U1, U2, U3 from that. So we get the finite binary words giving us the names. So basically ordinary binary representation gives us names by cutting it off at different finite lengths, going longer and longer as you go through. So it's easy to see that this is surjective. And secondly, I want to just observe a property that follows from the rapid Cauchy definition, which is that if U0, U1, U2, U3, so on, this is the sequence of names of dyadic rationals that represents a real number. So if this is a name for X, for a real number X, so what does being a name mean here? Well, it just means that this is mapped to X by the representation. So the same terminology as before that we were using for representations, we're now using infinite. It's an infinite name for the real number X. Then every U sub I is within the rapid Cauchy property doesn't just guarantee that the members of the elements of the sequence themselves are within 2 to the minus n of each other, but also the limit of the sequence is also guaranteed to be within 2 to the minus n, because the set of numbers that are within 2 to the minus n of another is a closed set. When you use a non-strict less than or equal definition as we did, so then the distance between n and u sub n and any u sub n is less than or equal to 2 to the minus n. So the rapid Cauchy property actually tells us how rapidly the approximations are converging to the number that they represent, little x. Okay, so I've said that the advantage of this representation over the ordinary binary or base 10 representations are that it works. So let's look at some of the properties that say that it works. It's actually not going to show any difference, but it's worth saying anyway. So if you remember, in 2 lectures ago, when we were first considering infinite sequences, we had the notion of a computable infinite sequence, which is an infinite sequence that can be output by a type 2 Turing machine that has no inputs. So a type 2 Turing machine with no inputs can just compute away by itself, that doesn't have an input tape, it can just compute away by itself using some algorithm to churn to spit out output characters, and if certain infinite sequences can be output in that way, for example, the decimal representation of pi has a very good algorithm that will output the digits of the decimal representation of pi. We had the notion of a computable infinite sequence. We now have the notion of a type 2 representation. We have a type 2 representation of the reals, and we say a real number is computable if there's if it has a computable name. So a real number is computable if there exists a real number x is computable if there exists a name for it u1. So I don't have a convenient note shorthand for these names, but anyway, it's okay. We can work with the longhand such that computable name such that the interpretation of that name and the Cauchy representation is X. In other words, if it has a computable name. So it's actually an interesting fact that's easy to prove in one direction, but quite requires a little bit of nasty stuff in the other direction. But it's an interesting fact that the computable real numbers with the Cauchy representation actually are the same as the computable real numbers with the base 10 notation or with the binary notation. Even though those are bad notations, they still give rise to the same notion of computable real number. So this is kind of the right definition of computable real number, but even if you make the wrong definition, in a sense, using a bad notation like the base 10 and the binary notation, you get the same notion of computable real number. So this coincides with computability for real numbers defined using base B notation for any B. Any B greater than or equal to 2. Doesn't matter which B you choose, you get the same notion of computable real number. So this now kind of brings us back to Turing's paper from 1936, because in Turing's paper, he defined the notion of computable real number, and he did so using base 10. I don't quite remember, but I think it's base 10 notation in that paper, but you know, the equivalent he used base 2, and it's the same as this notion of computable. But Turing in his paper defined the correct notation of computability for real numbers. But on the other hand, he then a little bit talked about computability of functions between real numbers, and only after the publication of his paper realized that actually these ordinary base notations have this defect that there are very simple functions you can't compute. For example, multiplication by 3, in the case of binary notation or base 10 notation, you can't compute those. So Turing realized that, and he had to publish a correction to his paper, where in that correction, a year later, he did something like, don't remember exactly what he did, but he did something like considering the base, considering the Cauchy representation. So for the notion of computability of a real number, actually we don't really need this new, better, as I've said, better notation, this Cauchy representation. But when it comes to computing functions, we do. We saw a significant defect in computing functions with the base 10 notation. The same defect applies to, or similar defects apply to any other base B notation. So let's at least see that we've solved that problem. And we can do that. So let's just, without further ado, we're going to have the function that multiplies a real number by 3 is computable now. So remember, we were using in lecture 3 a notation like this, saying a function on a represented space is computable with respect to a representation of that space. So it maps representation of the input space to a representation of the output space, meaning there exists a matching function on names that computes the underlying function on the set, the 3 times x function, by a function on the names. So again, I haven't defined in this lecture the notion of computability with respect to a type 2 representation, but it's exactly the same definition as for a type 1 representation. It's exactly the same everywhere, except that you replace the set of finite words with the set of infinite words, but there's no other change. So I don't need to write the definition out on the board. It just means there exists a function on names that computes the underlying function on represented elements. In the lecture notes, I have written out the definitions so you can look for the details there, but you try to adapt what was in lecture 3, you can't really go wrong. Now, because this Cauchy representation is kind of the right representation of the real numbers, when we talk about computability on the real numbers, so henceforth we won't refer to the notation, it's just going to be there implicitly. So the formulation I like of this is just, this is our default representation of the real numbers, and we simply say the function x, the 3 times function, is computable. So let's prove it. And this is very simple, so it's only going to require this little bit of space at the bottom of the board here. So our Turing machine, our type 2 Turing machine. So what it needs to do, we need a type 2 Turing machine that, given any word for a real number x, will output a word for the real number 3 times x. So where word means infinite word. So on input, an input word will be a representation of some real number x. So the input word, we're only interested in what the type 2 Turing machine does on words that actually represent real numbers. So it's going to look like this, where each use sub I is the representation of a dyadic number. And we need to say how the Turing machine is going to output. So what it's going to do, I'm going to not define this bit rigorously, but in the Turing machine, we implement the usual primary school algorithm for multiplication. It's not even long multiplication, it's simply multiplication by 3 on binary numbers here. We implement that on finite representations of dyadic rationals. There's an easy algorithm to multiply a representation, a finite string representation of a dyadic rational number by 3. You might have done something similar in exercise classes. So let's assume we've got the algorithm that multiplies a dyadic rational by 3, and we're simply going to return the sequence of multiples by 3 of these dyadic rational names, and that's going to be a Cauchy sequence converging to 3 times the number represented by x. On input, so this is an input representing x. So we output the sequence. So this is by 3 times u2, I mean the dyadic word computed by our primary school algorithm adapted to binary dyadic rationals for multiplying by 3. Here we have 3 times U3, 3 times U4, 3 times U5, and so on. So this is representing 3 times X. So it's pretty easy. The question for you, why did I start with U2 here?
This is the last process.
What's the last property?
It has to be smaller than 1 power minus n.
Yeah, so the rapid Cauchy. Did I call it the rapid Cauchy or the fast Cauchy property? Yeah, maybe in the notes it's rapid Cauchy, but anyway, rapid and faster mean basically the same thing. So if I didn't multiply it by 3, so sorry, if I didn't shift it, then we would break the fast Cauchy property, because U0 is only needs to be within 1 of the output. So the first term needs to be within 1 of the output, and if we multiply it by 3, we're only guaranteed to be within 3 times the output. But if we shift by 2, then we're improving matters. So then we do satisfy the property. Anyway, so that's really easy. And actually, not only is this really easy, but it's indicative of a general approach to computing continuous functions. In that, if you have a nice continuous function, that you have a nice way of computing sort of how it works on dyadic rationals, actually even from dyadic rationals to real numbers rather than dyadic rationals. Here, the 3 times function preserves dyadic rationals, but I mean, in any case, one can adapt this method to really. So although here we're only doing the algorithm for 3 times x, actually all the usual continuous functions that are, they only have to be continuous on their domain. So the functions with sort of singularities in them are also okay as long as they're continuous on the domain of definition. All the usual functions from analysis turn out to be amenable to this kind of, so all the trigonometric functions, exponential functions, and so on, they can all be computed exactly using this representation. So that's a nice situation. I mean, 3 times x is obviously very simple, but we've got a good representation that one can essentially do everything one wants to do mathematically with the real numbers, compute it exactly, compared with floating point arithmetic, which is how people normally compute with real numbers on a computer. This has the significant advantage that you never go wrong. So whenever you want to get your output with any degree of accuracy, you just have to ask for it to compute sufficiently far. Of course, there's a big disadvantage with this approach if you actually come to implement it. I guess somebody can guess what it is. So why don't well, memory use is part of it, yeah. So it's just in general. Sorry, what you? Oh, well, there's the infinite, but in a sense, the infinite is mitigated by you having, whereas infinite, you still have an algorithm that so for example, outputting pi, it's infinite, but you can still have an algorithm that will output it as far as you want. And you can sort of pipeline these, process that inputs an infinite stream to another process. So one can get around the infinite aspect. But I mean, that is related to the problem, and memory usage is a problem. But I mean, more generally, it's just inefficient. So whereas floating point arithmetic is in a fixed amount of memory, it's been heavily optimized over decades. Even your processor chips are optimized to do floating point arithmetic. So this is working with arbitrary memory, and it's slower, and so it's significantly slower. It hasn't been optimized in hardware or anything. Some people tried to look at that in the 90s, but it didn't really get anywhere. So it's much more inefficient. But if you're in a situation that you want to know that a computation is accurate, and you don't want to do the error analysis for yourself, to be sure about using floating point arithmetic, then this approach is, people do actually use it in practice in certain circumstances. Right, good. So that's So these are somehow, it's the main idea here. We've got a representation, a good representation of the real numbers that allows us to compute the functions that we really want to compute mathematically, and it is practically useful. So what I want to end with, the last big result of the course, is a mathematical result about the functions that are computed in this way. So it's 10 to 4. What I'm going to do is I shall state the result, and then we'll maybe have a little lemma or something that's going to help us prove it. Then we'll have the break, and we're only going to take 15, 20 minutes after the break, and then that'll be it. So I wonder if anyone can guess what the theorem is going to be. It's similar to something we've seen before. Any guesses as to what our theorem is going to be?
There are things that are just partial of the first
It's going to be a constraint on what functions we can compute. Of the topological nature.
maybe the continuous functions or those with x4.
So indeed, it's related to continuity. So we can't compute every continuous function because there are many continuous functions, and we can only compute countably many functions because we've only got countably many different type 2 Turing machines, but every function we can compute is continuous. So for the theorem, the last main result of the course, so if a partial function is computable, then it is continuous. We're talking about partial functions being continuous. So again, by continuous, I mean it's continuous on its domain. So continuous on its domain. But that means the same as, I didn't use that terminology in the last lecture, but it means it's continuous with respect to the subspace topology on the domain of the function, i.e. f is continuous from the domain to subset of real numbers to the reals with respect to subspace topology. It's useful to look at partial functions because lots of functions of interest are partial, such as, I mean, a very simple example is the reciprocal function, 1 over x, is not defined at 0, the partial function, but is nonetheless continuous on its domain. So everywhere on the domain of the non-zero numbers, it's continuous. And indeed computable. And so again, this is just a one-direction theorem. It's not true that every continuous function is computable, but on the other hand, the functions one typically encounters in mathematics, apart from when one has an example of a non-continuous function, but such things are often counterexamples. But the functions that naturally occur in mathematics are continuous on their domain. So the vast majority of functions that naturally occur in mathematics are continuous on their domains, and those naturally occurring functions all turn out to be computable. So it's a good collection of functions. So there are some functions that are not computable, like the indicator function or the characteristic function for so the sign function on a real number, but assigns -1 to a negative number, 0 to 0, and 1 to a positive number, that's a non-continuous function, so that's not a computable function. That's a useful and mathematically useful function that's not computable. And can't be computed. Right, so we want to prove this. We're going to prove it using the fact that continuous functions that computable functions on infinite words are continuous in the sense of the previous lecture. And so I was going to give you a lemma before proving it, but actually rather than doing that, I'm going to do something similar to what I did last week. I'm firstly going to give a high-level quick proof of this for those that like abstract topological arguments. And then after the break, we'll go into a low-level direct proof of this. So it's going through the details rather than the topological shortcut. So the high-level quick proof of this is as follows, although I'm not going to prove the claims I make. So this is just for people who know the topology. High-level quick proof. So the high-level quick proof is that actually the function gamma c from the domain of gamma c, from its domain, which is a set of infinite words. So this is now a total function to the reals. Total surjective function to the reals is a topological quotient. So you need to prove that. But anyway, it can be proved. And once we've got that, so suppose f is a partial function is computable. So then we have we can write a diagram where we have the domain of f, and f goes to the reals. Here this is represented by those names, but every real is represented by a name. That's the domain of the domain of the Cauchy representation. Here we have gamma sub c. In the top left corner, we have what's the best way to describe this? So we want all those representations that are I didn't prepare for this. I thought it's so what we want here are all representations of real numbers that represent elements in the domain of f. I'm just trying to think of a nice way of writing this other than telling you it's a pullback. So,
That's quite level.
well, that's true, but so let's put it like this. So P in the domain of gamma c, let's just write it straight in the as I said it. So such that f of gamma of gamma C P is defined. So all those representations of real numbers on which that represent a real number such that F is defined. So if it's computable, being computable is saying there exists a computable G such that, so here we have again gamma C, restricted to this, but it's defined on this by the way I've defined this. So then we have a computable G. This is the quotient map by topological generalities that we're this can be retains the pullback of a quotient map under a subspace inclusion. So it's again a quotient map. Pullbacks in general, quotient maps are not quotient maps. Anyway, this is a quotient map, and we have a diagram that commutes where we have this is continuous. This is continuous. This is the quotient, and we have a diagram of functions that make this compute, and because it commutes and because this is a quotient, this is a continuous function. So F is therefore continuous because the left-hand map is the quotient. But I'm sorry, you really don't need to understand this argument. And it occurred to me while I was writing it out that I really should. In fact, I did plan to check for myself just before the lecture that this map here, when we restricted the domains, is still a quotient. I mean, it has to be, but I didn't actually have time to because something else cropped up before the lecture. But anyway, it doesn't really matter because this is the abstract argument that I was filling time with because now it's time for the break. And after the break, we will do the direct argument for a short. It's probably going to be just as quick because I've spent rather longer than I planned to on that. But anyway, we'll do the direct argument, which is all you need to understand, and that's going to be then the end of the material course. Okay, so we have a break. It's again round about 4 o'clock, so we shall start again around about 4:15. Thank you very much. I think it'll be about 20 minutes from now, then it's going to take. Okay, so having given you a quick and abstract proof of this theorem, and I want to do the nuts and bolts, the nuts and bolts proof of the theorem from first principles. So to do that, let me introduce the following notion that we say a name. So remember, our names for real numbers are these infinite sequences of representations of dyadic rationals. So a name for a real number x is closed. So if we have this rapid Cauchy property that told us that every u sub I, the implication of that is that every u sub I is within 2 to the minus I of the number x. We're going to say it's closed if the approximations are twice as good as they need to be. So it's closed if, for all I, the distance between the dyadic rational represented by u sub I and x is, well, it's guaranteed to be within 2 to the minus I, so 1 over 2 to the I, but we say that it's closed if actually it's within, it's twice as close as it needs to be. Okay. So the rapid Cauchy property is giving us these, well, we know how close these things need to be, but for a closed name, they're even closer than they need to be. And the lemma about closed names is that firstly, every x has a close name. And secondly, so let's call that one. And secondly, a slightly elaborate property, not very elaborate, but let's prove one first and then go on to property two. So these closed names, we already have that every real number is represented by some name of the sequence of dynamic rationals that enjoys this fast Cauchy property. In fact, you can always find a close name, and that's very easy because let U0, U1, U2, and so on be a name for x. Okay, here's a test for you. See if anyone's awake with this. Can anyone see a way of immediately converting this to a close name?
Just shift to the left.
You just shift to that. We just drop the U0. So the same trick we already used the multiplication by 2. So then U1, U2, U3 is a close name. So that's very easy. So what's the benefit of close names? Well, the property we're going to use of it is the following, that suppose U0, U1, U2, so on is a close name for x. And suppose we've got another real number x prime, where the distance between x prime and x is less than or equal to 1 over 2 to the n plus 1. But the point is, so the idea of a close name for x is going to allow us to do the following thing, that any close, if we've got an x prime sufficiently close to x, and we've got a close name for x, then we can modify the name for x to get a name for x prime, keeping the first n approximations that we already have. Because they're sufficiently close, they're also going to be close enough to x prime to still be named. So it's no longer guaranteed to be a close name for x prime, but it will at least be a name for x prime. So then there exists a name for x prime of the form. The point is we can keep the, well, when I say the first n, it's actually a prefix up to and including un. So of the form U0, so we keep the same starting prefix that we have for x, up to U n, and then obviously we can't continue because at some point we have to start approximating x prime rather than x, but we can go as far as the un term for x prime, for approximating x, and then we diverge, and now we need some other continuation. But the point is we can keep the initial prefix that we have for x, because it's close enough also, it's close enough to x that there's some room to make it that it's still sufficiently close to x prime. So that should be an n plus 2. And you know, the time is ticking on, so this is not difficult. So let me just, if you're interested in seeing a proof, I mean, it's the sort of thing you can work out for yourself, but let me just say, see latex notes if you want to see the argument. Essentially, the idea is the original name, because of this closeness property, it's an x prime is within a certain distance of x. We're not getting far enough away for this to break the required, for this prefix here to break the required approximation properties. Then it's easy to add a caret to get at the end approximations to x prime. Right. Okay, so now we're going to prove maybe I'll just move the camera. And now we can prove our last theorem of the part of the course that is going to be written examinable. So the proof of the theorem. So suppose f is computable. So partial function from reals to reals. And let, if it's computable, that means we have a computable function on names that computes f. So let g be a partial function on names, so that's partial function from Cauchy alphabet, infinite words over the Cauchy alphabet to infinite words over the Cauchy alphabet. That realizes f. So given a name for an x in the domain of f, g applied to that name will be a name for an element of f of x. We want to show that f is continuous. So to show f is continuous, we're going to do the usual thing from analysis. Take any epsilon, consider any x belonging to R, belonging to the domain of f, and an epsilon greater than 0, and we want to find a delta around x such that f applied to anything within delta of x, it lands within epsilon of f of x. So we need to find delta greater than 0 such that for all x prime in the domain of f, if we have that if x prime is within delta of x, then f of x prime is within epsilon of f of x. Okay, so all familiar stuff from analysis. So how are we going to find this? So we've got our x and our epsilon. How are we going to find delta? Well, to do that, we're going to use these fast names. So this, the point of introducing them is that we need to use them in this proof. And we will see why we need a fast name a little bit later on. But because x is a real number in the domain of f, it has a fast name. So let u0, u1, do I call them fast names? Closed names. So be a close name for x. And now what we're going to do is we're going to look at the output sequence of f applied to this name, this close name. I just want to, yeah. So let's call this P. This close name. I just want to see how I write this next thing. So because x is in the domain of f, and P is a name of x, and G computes f, G must be defined on the name of P. So G of P is defined, and because G computes f, the value of G of P must be a name for f of x, and is a name for f of x. And because it's a name, I think I call it these in my notes.
and call it. So let's call it R. So this is what we get by applying our function that computes f on names to the name p, and that's going to be some name for f of x. So that's going to be of the form v0, v1, v2, v3, and so on. And now we want to show that any x prime close enough to x is going to, if we apply f to it, we're going to get close in, we're going to be within epsilon of f of x, where f of x is the real number represented by this name here, R. And to get things to work, we're going to look at we want to look at a neighborhood of f of x, essentially determined by fixing a prefix of r that's sufficiently long. In the end, we want to be within epsilon of f of x. And the thing that's going to work, it's like with these proofs in analysis, you always have to find the right epsilon or epsilon over 2 or epsilon over 3 or things that if you remember from courses on analysis that make things work. And what works here is we let, I'm going to call it capital N, be such that 2 to the minus n plus 1. Let me.
Do I write it like this, or maybe I write it?
Well, it's the same thing, but anyway, let's do it like this. 2 to the minus n is less than epsilon over 2. Okay, so we make n sufficiently large. And the point is that if we look n steps along the v's, so we go up to capital N here, then any continuation word is going to give us a name by the first Cauchy property, is going to give us a name that's within epsilon over 2 of f of x. So the prefix of the first n element, n these is going to be important, and we'll write n for the length of that. So n be the length, that's the number of characters of the finite word, which is the prefix, b0, b1, all the way up to b capital N. So G, when applied to our name for x, u0, u1, and so on, gives us this infinite word here. By the continuity theorem from last week, 2 weeks ago, but the last lecture, there's a finite prefix of the u's, such that when we apply G to any extension of that, we will get the finite prefix of length little n of the output, which will give us all the dyadic names v0 up to v7. So by the continuity theorem from last week, by lecture 11 continuity theorem, there exists some little m such that any input sequence that agrees with p on the first little m characters will coincide with f of x, will coincide with g of p on the first little n outputs. So we'll have the same prefix up to little n. In fact, we'll have the same capital N terms here. Now, little m may land sort of midway in one of these input, in one of these dyadic encodings here,
which is a bit awkward, but we can always then go along to the end of that dyadic encoding. If we've got more input, we're still going to have the same property. So to cut things a little bit short, there exists a capital M such that for any P prime with P prime restricted to little m, where m is the length of U0, U1 up to U sub m. We have that G of P prime, the first little m characters of that will be the same as the first little m characters of G of P, which is V0, V1 up to V of capital M. Okay, so by the continuity property from last week, we have a finite prefix of the Cauchy sequence of dyadic rationals, such that when we apply G to any extension of that finite sequence, we'll get the same first n output dyadic rationals. But then we're going to use now the fast Cauchy property.
Move camera, please.
Yes, thank you. I was just actually moving to the remote control when you said that, but it's always good to be reminded just in case I don't always remember. But anyway, there aren't going to be many occasions to remember or forget from now on. Right, so by the fast Cauchy property, so fast Cauchy, no, by the close name property is what I mean. If we have any x prime that has distance epsilon over 2, but that has distance within epsilon over 2, then x prime has a close name, sorry, has a name of the form U0, U1. So the point is U up to capital M. We've chosen things in such a way that any x prime within epsilon, sorry, this is not right. Not epsilon over 2. 2 to the minus capital N, sorry, capital M plus 1. So this lemma, by property 2, this lemma here, any such thing will have a name that begins with the same prefix U0 up to Un. Then you go to U prime n plus 1, U prime n plus 2. So some different continuation. And we see that G applied to that name, so this is P prime. Then G applied to P prime has the form, well, first little m characters, it starts off V0, V1 up to Vn. So it starts off V0, V1, V2 up to Vn. And then it continues the V prime n plus 1, doesn't matter really how it continues. The point is that it has the same prefix here, and because it's a name, we know, because this output is a name, we know that this is within 2 to the minus capital N of
of two, we know that this is within 2 to the minus capital N of f of x. So, which is a name. So, which is a name for f of x, sorry, which is a name for f of x prime. It's because p prime is a name for x prime, and so because G computes f, G of p prime is a name for f of x prime. So by the property that's guaranteed of names, so the distance between f of x prime and f of x, well, we've got the same starting prefix as far as b1 to bn. So this is within, two to the minus n is less than . Well, the point is that needs to be less than epsilon, and it must be very obvious. Well, it's not a good way to end the course, is it? I mean, everything looks like it should fall into place, and it must do. And I haven't been referring to my notes, I was kind of going on autopilot through the. Can anyone see the? I mean, the thing is, you should get two distances of epsilon over 2. So we've got that.
So f of x differs along the number not described by Bn by e over 2, and f x prime also differs from that number by e over, and then by that because
Right. Good. Yeah, that's. Yeah. Good. So. Yeah. Thank you. So this should be the rational number, should really be so QD of the n. And f of x minus d of the n is less than epsilon over 2. Right, good, because thank you. Very good. Because Vn is here the nth element of the approximating sequence for G of P, which is a name for f of x, and the nth element is always within 2 to the minus n, and 2 to the minus n is less than epsilon 2 here. So that gives us this,
but it's also the nth element in a sequence that's approximating g of b prime, which is the name for f of x prime, so the same argument gives us here. And so the two things add up. So thank you very much for saying it. It's well, let me put it down to too much New Year celebrating or something like that. That will have a certain amount of energy for the lecture, but at the end it kind of fizzles out. Anyway, good. So thank you very much for helping me out at the end there. Let's end the Zoom. So thank you very much. We can end the recording now.